Hey everybody, in this video we're going to review the notion of an equivalence relation. So let's start by taking a look at this map. And in the map you'll see houses, right? These are individual houses. And it matters, right? The difference between houses. If you come home and go into a random house in your neighborhood, odds are it is not your house and the people who live there are not going to be super happy. So it really matters the distinction between these houses. On the other hand, if somebody wanted to send you a package, they're going to give an address to, say, FedEx, and in terms of how FedEx is going to get that package to you, the itinerary isn't really going to care which house you're in on this block. It's mostly going to, want to know, okay, well, which state is it in? Which city is it in, right? And only once the truck actually gets to your neighborhood do they actually care which house you're in. But for a lot of purposes, like it doesn't really matter which house on the block you're in. Or alternatively, let's say somebody asks you where you're from. Now, depending on the context of this conversation, your answer might be very different. For example, if somebody in the neighborhood is asking you, then sure, you're going to tell, well, I'm 4 houses down. On the other hand, if you are going away to school and somebody says, hey, where are you from? Well, if everybody is kind of from the area, then you might not care about it being so close, and you might want to zoom out. Okay, so let's zoom out a little bit here. So I zoom back out, and eventually you notice I can't see the houses anymore, and maybe I go out even a little bit further, and all of a sudden you just start to see the cities. Right? So somebody says, where are you from? Well, I'm from Fullerton, right? Or oh, I'm from La Habra. Right? They're not really interested in which specific street in La Habra you're on and which specific house on that street in La Habra you're on. They just care that you're in La Habra. Of course, if you maybe go away to another part of the world, then they might either be asking you, where you're from, and you just would say, okay, well, let me back it up, and all of a sudden the cities don't really matter so much. Maybe now we're just talking about the states. Well, I'm from California, right? Oh, I'm from South Dakota. Or if you really are going around the world, maybe they don't even care which state you're from, right? You say, well, I'm from Mongolia. Oh, I'm from the United States. Oh, I'm from Algeria. All right. So the whole idea here is that sometimes it is reasonable to treat things that are demonstrably different, like which house you live in, as if they were the same. All right, 2 houses on the same block, we really don't care about that difference if we're asking which street you live on or which state you live in. And that's going to be the underlying idea of an equivalence relation. Okay, so let's do an example here. I've taken a set that has 12 elements in it, and I've pictured it with just these 12 dots. And I've arranged them into a pattern which hopefully will be suggestive. I want to put an equivalence relation, whatever that is, on these dots. So what we saw before is that when we put an equivalence relation on something, what we're doing is treating things which are different as if they were the same. Right? So anything that's going to be an equivalence class will be the same, even though we know underlying, right? They're really different. So the way I'm going to do it is by drawing some circles, or ovals really, around the columns. So there we go. I've just put a little oval around the first 3 dots, right, vertically. And what I'm going to be doing then is treating all 3 of these dots as if they were the same dot. So I really am just going to think of them all as this one superset of all of them. Okay, and then I can do the same thing with the next column, and with the next column, and with the next column. Okay, and if I had given names to these, like maybe this could have been an A, a B, and a C, then what I want to do is write down that A is equivalent to B. And we're just going to use this symbol here in the abstract. Later on this course, we're sometimes going to use this triple equal sign, maybe with a little extra notation. So we can use either one of these. So I would say that A is equivalent to B, and of course it's also A is equivalent to C, and also B is equivalent to C. Of course, I've written them sort of in alphabetical order. There's no reason I couldn't write it in the other way, right? I could write B is equivalent to A, and C is equivalent to A, and C is equivalent to B. All right? Now, one thing you might notice here, if I write these in maybe a slightly different order, if I know that A is equivalent to B, and B is equivalent to C, then it should be the case that I can connect up A with C. So this should imply that A is equivalent to C. Okay, and there's one more sort of obvious thing that I didn't write down, which is that an element should be equivalent to itself, right? So we could write this down. Of course, I could write the same thing with B's. B should be equivalent to B, and C should be equivalent to C. Okay, well, what do I mean by equivalent? Of course, I mean they're in this same oval. All right? So they're just in this same set. So how do we make this formal? Well, in class, we defined first a relation, right? Here we're doing equivalence relations, so it better be some sort of a relation. And remember that if you had some set S, then a relation on S is a subset of the Cartesian product, right? Remember, this is the set of all pairs. Some pair R comma S where both R and S are elements of S. Okay? So our equivalence relation should be a relation. So an equivalence relation on S, right, on a set S, we should say, is a relation. Okay, and we'll use a, well, how about we have to give a name to this subset. Oh, how about we'll use I don't know, like a nice curly E, because it's going to be an equivalence relation. Is a relation E on S, right? So i.e. E is a subset of the Cartesian product such that, well, we need these things that happened above to hold. So first, so what is usually called the reflexive property is that if you have some element A in S, then A comma A is an element of the equivalence relation, or of the relation, meaning this is how we are sort of making very formal this idea of A is equivalent to A. Okay, so again, this is called the reflexive property. All right, second, well, we saw up above here, you know that A is equivalent to B, then you better also have that B is equivalent to A, right? If one of them is in the set then with the other, then the other should be in the set with the first. So if A and B are in S, such that A is equivalent to B, so that means that A comma B is in the relation, then B comma A needs to be in the relation. Okay, and this is sometimes called the symmetric property. I guess we want a second M there. Okay, and third, and this is the one we had up here, if A, B, and C are in S, such that you know that A is equivalent to B. So A comma B is in the relation, and B is equivalent to C. So B comma C is in the relation. Then A needs to be equivalent to C. So A comma C will be in the relation. And this is called the transitive property. Now there's an alternative way of describing an equivalence relation, which is very, very important, which is, well, let's go back up to the picture for a moment. You'll see what we've done is we've taken this original set and we've constructed 4 different subsets. And those 4 subsets, we might say, partition the original set, right? Every element is in one of those 4 subsets, and it's and every element is in exactly 1. Right? We'll get rid of this little red line here. So every one is in 1 and only in 1. So each dot is in exactly 1, and that's called a partition. And this is equivalent to having an equivalence relation. So an alternative formulation, right, and this is actually a theorem that you should prove, an alternate formulation is that an equivalence relation on a set S partitions S into disjoint subsets. Okay, meaning it breaks it up into subsets which have no intersection, and everything in S is in one of those subsets. All right. So this is going to be super handy. Equivalence relations are just absolutely ubiquitous in mathematics. We're going to use them just a ton this semester, probably most notably when we do modular arithmetic, but that's not going to be the only place we do it. So I'll have another video up where we talk more about treating the elements of a set, or rather treating these equivalence classes, right? These big sets here as the sets you're concerned with. All right, and so we'll talk more about some of the terminology, like sets of representatives and equivalence classes, etc. And maybe we'll do a few more examples. All right.